Hello. Welcome to week 2 of Physics 130. Last week we laid the mathematical foundations for the course, and this week we are going to get into the heart of physics, which is the physics of motion. And as you can imagine, that applies to the biological world in many, many ways, and we're going to start discussing that over the next several lectures and weeks. So the phrase that we usually use to describe motion in physics is kinematics. And so this chapter is kinematics in one dimension. It's much, much easier to deal with motion in one dimension before looking at it in 2 and 3 dimensions, because in 2 and 3 dimensions, we need something called vectors, which we'll learn about next week. Okay? Kinematics is one of those words where at first it's like really hard to say. You kind of trip over it, stutter a few times, but then after a while, you can totally say it 10 times fast. Kinematics, 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 kinematics. You get the idea. Okay, so guys, if you can click to the quote of the week. If you remember, I always like to add a quote at the beginning of every week's lectures that just kind of reminds us that we should always balance science with some amount of wisdom. Okay, this is a quote by the ancient Chinese philosopher Lao Tzu, who says, "Life is a series of natural and spontaneous changes. Don't resist them. That only creates sorrow. Let reality be reality. Let things flow naturally forward in whatever way they like." Okay, I think in layman's terms, this is Lao Tzu's way of saying, guys, life is hard enough with just the unfortunate things that happen day to day without adding a whole bunch of resistance, right? There's two kinds of frustrations in the world. There's the frustrations of the stuff that you can't help because they just happen, and then there's the frustrations of all the resistance and the rumination and the thinking about it that comes afterwards, and the why me, why is this happening, why does this have to be like this, right? He's saying the only sane thing to do is to accept life as it is, and once you accept it, you're empowered, you have the power to do whatever you can to either change it or make the best of that situation. Okay? If you'd like to know more about Lao Tzu, you can look him up on the interwebs. Okay, click ahead. The other thing that I like to do to start every week is to answer the question, why in the hell do we care, guys? Why am I teaching you this, and why do you as future biologists, doctors, physical therapists need to care about this? Well, this week, there's many reasons, but there's a very, very interesting theory about how life started on Earth at all. And one of those theories is that we are all Martians. Okay? No, hear me out. This is legit. So it is possible that in the beginning of the solar system, in the early days of the solar system, the conditions on Mars were slightly better for life than on Earth. Okay, and it is entirely possible that due to liquid water existing on Mars, there's some basic forms of life, some microbes that arose before they did on Earth. And it is also entirely possible that at some point a meteor came in, collided with Mars, which was happening a lot more frequently in those days, in the early days of the universe, and it is entirely possible that those microbes were thrusted out from the atmosphere of Mars and then slowly, due to gravitational attraction, coalesced and landed on the Earth. And that formed the basis of the life that we now see today on Earth. Okay? This is just a theory. I'm not advocating this, but in order to answer such a theory, we have to ask ourselves the question, could those microbes even survive the acceleration required to shoot them out of the atmosphere of Mars, right? By the end of this lesson, we will be able to find out exactly what that acceleration needed to be. That is my promise to you. Okay, if you guys could click ahead, we're going to start by answering the question, what is position, distance, and displacement? Okay, these are 3 terms that sometimes get jumbled up because they kind of sound similar. And we kind of have similar concepts or notions of them in our head, but I'm going to show you that they are all different and be very specific about how they're different, okay? So I'm going to start by making the number line as there is on this slide, okay? And in the middle, we have a 0. Over here, we have a 1. Over here, we have a 2. Over here, we have a 3. Over here, we have -1. Over here, we have -2. And over here, we have -3, okay? Now, your position is just simply where you are in space. So let's say that I, Scott, am just sitting here at the origin, 0. That's my position. My position is 0. Okay. Let's say that I decide to go over here to 2, right? In that case, my position is 2, okay? Very simple. Let's say that I decide to come back here to -2. In that case, my position is -2. So it's just where you are in the plane. This isn't just one dimension, but this also works if you have 2 dimensions, right? So let's say that we have a y-axis and an x-axis, and I'm over here at 2, 1. So in this case, Scott's position would be 2, 1. Okay? Very basic. Distance is a little bit different, okay? In the case of distance, you are summing up the total amount of space traveled by that object, okay? So for example, in this case, if I go from 0 to 2, I've traveled 2, right? If I travel from 2 down to -2, I've traveled 4, okay? Notice I'm not putting a minus sign here. I'm just adding up all the distance I traveled, whether it's backwards or forwards, okay? And I get a value of 6. So in this case, 6 would be my distance traveled, okay? Again, I don't worry about the sign. Distances are always positive because distance is something called a scalar, which is something we'll talk about next week. Okay, now displacement is a little bit different. Displacement just asks the question, what is the difference, the simple difference between where I end up and where I started, okay? So if I ended up at -2, but I started at 0, then my displacement is -2. In this case, it is important that I keep that negative sign because displacement is called a vector, and with vectors, direction is important, okay? So let's do a quick example, okay? Let's do the example of Scott just jumping up and down, okay? So I'm going to summon all the strength that I can possibly muster in my soul and do the highest jump that I can possibly do on this video. Are you ready? 3, 2, 1. Okay, so that was approximately 1 foot of a jump, okay? So in other words, I went up 1 foot, and I went down 1 foot, and it's not SI units, but I don't care right now, okay? So my distance in this case would be, very good. If you said 2 feet, you are correct, okay? What would be my displacement? And if you said that the displacement would be 0, that is also correct. Because the difference between where I started and ended is the same exact position, so I haven't actually moved, so my displacement is 0, while my distance would actually be the full 2 feet of me moving a foot up and then a foot down. Okay? Does that make sense? All right, so this is the foundation of position, distance, and displacement. In the next video, we're going to begin talking about how we graphically represent these and how we just look at motion on graphs. Okay? I'll see you there.